If you look at the algebraic equation like this, and you know extra, let me just zoom. If you know extra that all coefficients are reals, not complex anymore, but reals, then you know that for every z which is a solution, the complex conjugate will also be a solution. That's the statement of the lemma. And that's the one which actually tells us that every time you have a root, you will have a complex conjugate of that root. There's a little proof to this lemma. In the lecture notes, you have a proof. You can have a look at that. In fact, I think there is a question in the tutorial books which is of a similar nature, although the question there operates with a degree like 3 or 2 to make it a little bit easier. Whereas the proof which I gave in the lecture notes, the handwritten one, works for every degree. Because one of you, in fact, when he came to the tutorial, he suggested a proof which works for square polynomials, which was a good proof, but it didn't work for any degree. Now, for any degree, the proof actually handwritten proof in the notes which I gave to you, which are the notes on the Moodle. Now, there's a little consequence of this lemma, or corollary. That's like official name for the consequences in mathematics. As the one which was like suggested by one of you just now, is that actually when you look at the polynomial of odd degree, like 5, well, you can't have enough space for couples there, right? If roots comes with couples, you will have even number, right? How are you going to accommodate this odd degree of the polynomial if they come in couples? Yes. Or you, like in the roots language, you're saying that one of them should be real number. Yes, that's the one of the. It's a very proper observation. In the polynomial of odd degree with real coefficients, there must be one which doesn't have a couple. But the number which doesn't have a couple, it's a real number. And it's a powerful consequence. In fact, and here it is. It says this. If I open it, if you have real coefficients in the equation up there, and degree of this, and degree of your polynomial is odd, like so, then there must be, remember, exist, and this time it is a real number, which is a solution to this polynomial. Powerful consequence which says to us every polynomial of odd degree with real coefficient must inevitably have real solution. In analysis part of this topic, you will learn, well, you need probably exercise a bit of a intuition and self-thinking for that, but you will learn alternative proof to this conclusion on a pure analytical basis, because this is the algebraic proof of that. In the analysis, you can prove this by totally different methods. Continuity, intermediate value theorem, and something like this. And that answers the question with the degree 5. With the degree 5, there will be roots and couples, and will be one real all the time. Again, we don't have a method how to find that in general, but there will be one.